This is a project through Stride, which ended earlier this year. We did do 2 phases of this project, and we'll kind of go through both of those through today's webinar, just to make sure everybody's up to speed on kind of where this whole project in question originated from. Okay, so the agenda that we're going to go through, we'll do some brief introductions. We'll go through a background, methodology, and results, and talk about next steps, and that's all related to phase 1. And then we'll talk about what we did in phase 2, based on kind of the future work that we thought needed to be analyzed deeper and worked on more from phase 1. And then again, we'll take questions at the end. Okay, so the project team, so Narmina and myself will be presenting today, but we are not the only ones that worked on this project. We have additional team members from NC State. We're Kai Monist, Jonah Friedman, Wal Wright, and Kevin Hart. So there were, as I stated, we did a phase 1 project, and some people in attendance today may not be familiar with phase 1. So the first part of this presentation is going to be kind of give an overview of that process to kind of set the stage for what we did in phase 2 and why there was a phase 2. Okay, so what was the motivation for this project? So school and public transit buses have the perception of being the cause for congestion delays, and we're not addressing that concern today. However, in order to understand if that is true or not, we need to determine and understand where school and public transit buses are most experiencing high levels of congestion delay. So some questions to kind of ponder as we go through these slides today. Something to think about: how many hours of delay does your agency experience from recurrent congestion? How much does this delay cost annually in terms of operating and capital replacement costs? Where should you target efforts to address recurrent congestion? And then how does delay impact your ridership, which is a featured research? A couple of these are featured research, so the target is also featured research. So we don't address all of these today, but these are things that you kind of want to think about from your perspective, things that we thought about when we were trying to determine how to go through this project. So just a little background. So these are things that we're all familiar with, but roadway congestion creates delays and increases costs for all users, and that includes transit and school bus operators. I mean, that also includes, every one of us who are driving ourselves to work or to school or to the grocery store, anything like that. Increasing the school bus and public transportation use decreases congestion. So ideally, the more people we can get on the buses, the less single-family cars there are out there, which would help reduce congestion. There is a mode shift from school buses to cars, and this can increase morning peak period congestion. Buses operating in areas with current congestion face increased costs to maintain existing levels, so they've got to add more buses to the road, which increase costs and also increase congestion because there's more vehicles, and this makes it a decreased market and competitive, which results in fewer people wanting to ride the bus. So it's just kind of this positive reinforcement or negative reinforcement in congestion. So phase 1 was a project that was undertaken through our group at ITRI, the Institute for Transportation Research and Education at NC State, and the University of Florida Transportation Institute. And we looked at both study areas as part of the phase 1. And we both have expertise in pupil and public transportation. So this is all familiar. There's just a couple pictures kind of showing what we're all aware of. In the top left is school bus stuck in traffic, and you can see a couple school buses. And then in the lower right, taken, I think, Seattle Times, we see a public transit bus in the middle of congestion, along with a bunch of other cars and trucks. And so what we're trying to do through this project is address when and where these high congestion corridors are occurring. So there are ways to address congestion delays that school and public transit experience. But we have to understand when and where they exist before a proper solution can be chosen. So each of these treatments that you see here, they do offer advantages and disadvantages, and it's up to transit planners to find the most appropriate solution depending on where the issue is occurring. And hopefully the results of this research can help transit planners do that. So here's just a couple of different types of treatments. One is bus on shoulder. Another could be route diversion. So if we know where there's high congestion, we can reroute a bus. This could be in a couple different ways. Maybe you're using that information to route in advance so that they avoid that to start it. But it could be if there's a massive accident, if you're doing that on demand, that's another type of diversion, route diversion. Bus lanes. So this allows buses to get out of the flow of traffic to pick up and drop off passengers. Queue jumping. So allows buses to jump in front of cars and kind of take priority. And then we have signal prioritization, where buses have a fob on their vehicles, the sensor that lets the light know that they're coming, and basically gives them priority through the intersection and allows them through. And so there's a couple places I know where that's existing. So again, these are all possibilities. It just depends on the infrastructure where the issue is occurring. So the project objectives. So we want to calculate the minutes of delay per roadway segment per vehicle for each hour of a typical day by mapping school and transit routes onto traffic data. From there, we calculate the cumulative impact on school and public transit buses, and then we can identify the segments with significant impacts. And once we have that picture, we can quantify the costs of congestion on the bus systems. And then ultimately, our goal is to make these results available to, for two reasons. One, to educate public officials and private citizens on the impact of congestion on public buses, but also to prioritize where to target treatments and enhancements to help alleviate some of these congestion issues that buses are dealing with. So why do we combine transit and school buses? So both of these systems have a lot of similarities to each other and are dealing with the same congestion issues. They're both usually publicly funded. They both have standard routes and times, so they're essentially fixed route services. Increased use of both has societal benefits. They do both experience negative impacts from recurrent congestion. School children related arguments for addressing congestion will add to transit approaches and may be more impactful in the public policy arena. And both agencies may benefit from working together to identify common concerns. For the site selection, so we worked with Florida. So we wanted to choose two sites, one from North Carolina and one from Florida. And some of the criteria that we looked at in determining where the sites to select were land use and densities, and make sure that they vary within the service area, that congestion is recurring, and that the school districts and the counties have common data sets. So this was a very important part in order to develop the initial methodology, was to ensure that the two sites we had the same data sets, so we could just create a single methodology. And in our case, those three data sets were the congestion data, which is archived by the Regional Integrated Transportation Information System, or RITIS. On the school side, public schools use school bus routing software from Education Logistics called Edulog. And then for the transit agencies, those data are cataloged through the General Transit Feed Specification, or GTFS. So based on these three criteria, the two sites that we selected were Durham County in North Carolina and Pinellas County in Florida. Okay, so the study approach that we took, so we worked closely, NC State and University of Florida throughout the project. The way that it kind of fell out was we were able to obtain the data first here in Durham, North Carolina. So we worked on developing the methodology and the analytical processes for Durham, and then used that method that we created to see if we could apply that to Pinellas County once they got their data and determine how easily replicable this method would be. So we went through that, and what I'll show you today in terms of the results are for Durham County. So they are specific to Durham County, but not limited to. So we did the same process for both Pinellas County and Durham in the end. So a little bit about the three data sets. So the first one is the congestion data. Again, Regional Integrated Transportation Information System. So it gathers traffic volume and speed data from a variety of sensors. It enables users to create roadway congestion profiles by day and time of day. And one of the drawbacks was it's only available on segments with sufficient observations. So you'll see later how this kind of impacts the final results. But it was an issue that we dealt with and something we thought about when we started working on phase 2 and how to address those concerns. On the school bus side, again, we used Edulog. It's a common school bus routing software, but it is not the only one. So there are several others used throughout the country. We have staff at Entry that are very familiar with Edulog and felt very comfortable using that software as part of this process. And it provides extensive information related to the planned daily bus route operations. And again, we have a group at Entry that supports Edulog implementations across North Carolina. So that familiarity was important to use that for the school bus related aspect of this project. And then finally is the GTFS, and that's the General Transit Feed Specification. So this was developed to make transit schedules and frequencies available through Google. I'm sure most of you are aware with Google Maps and logging on and seeing school bus and rail and routes showing up and scheduling, things like that. And so that's become a standardized software across the country. Most systems develop that, and actually as part of NTD, now have to have a GTFS, so it's even more synonymous across fixed route systems. So the just kind of a generalized methodology. So going to give kind of a high level overview of phase 1 and phase 2. We're not going to dive into the details. There are a lot of details that were part of this process, part of developing the final results. It is available in the paper, and we're also happy to discuss further offline if anyone is interested. But for the RITIS data set, we averaged that information into hourly profiles. So we took just typical weekdays, Tuesday, Wednesday, and Thursday. So we didn't include Monday or Friday or the weekends, which may have slightly different kind of travel patterns than we would see for the middle part of the week. We also avoided major holidays. Pinellas County has a lot of tourism, so we had to try and find a time there where that would not necessarily impact that. So we wanted to base this on what we would think of as a typical day. And ultimately, we decided on a date range that was between October 15th and November 14th. So we worked on this project during COVID, and obviously traffic patterns were vastly different during that time. So we wanted to go back to pre-COVID times to get what we would think of as typical travel patterns and expect to see at some point. Maybe we're back there now, I don't know, but that's why we chose 2019 at the time. Bus routes, so this is school bus routes. They're assigned based on an estimated route midpoint time. School bus routes have longer travel times, so it was a little difficult to figure out exactly which hour to assign them to. But we just kind of settled on this rule that if the bus start time started less than 15 minutes past the hour, that it would be assigned to the current hour. Otherwise, if it started after 15 minutes or greater than or equal to 15 minutes after the hour, then it would be assigned to the next hour. So if the bus started at 8:14, then we would give it the 8 o'clock hour. If it's 8:16 or 8:15, we would assign it to the 9 o'clock hour. I think that can be changed. That's just kind of how we chose to assign those buses to the hours. On the transit side, they have run times as well, and we just assigned those to those generalized run times. So the methodology too. So for what we did was with these 3 data sets, we started with the schools, created the routes, and once we had the routes in place, we could calculate the frequencies of school buses by hour of the day. And then we did a similar analysis for the public transit, and that gave us the frequency for our 2 bus systems. And then on the RITIS side, we calculated the congestion data by hour of the day. And so with these 3 data sets, we were able to then calculate the bus delay and frequency by segment by hour. One part we're going to go into a little bit of detail here is related to the segmentation, and this was a a difficult process that we went through, and it took a while to figure out how to get through this. So this might highlight some of those complexities that we dealt with. And we'll talk more about this when we get to phase 2 and how we address those and removed some of those issues. So here we have a simple street level example. We've got a horizontal line that we're calling our primary street. And then the 4 vertical lines, the 2 pointed up and 2 pointing down on the right-hand side, are secondary roads or local roads. So they're not primary. So the point here is that the primary road, the horizontal line, will be the line where we have congestion data. And so in this picture here, we've essentially moved the vertical lines. They're grayed out because we don't have any congestion data associated with those segments. So that leaves us with the sole horizontal line. And what you see here is the RIDIS segment along with its endpoints. And RIDIS data is not segmented at every intersection. So it might cross one or more or multiple intersections from the beginning of its line to the end. And so the travel speed is then recorded for the entire segment and not those individual parts. And so we'll talk more about that issue and how we address it here. In this example that we're going to look at, we're estimating that this length here is about 5,000 meters long, and there's about 5 minutes of delay incurred through this segment. The other point I'll make is school transit and buses often travel on these gray vertical lines. They don't travel solely on the primary roads. They do travel on secondary and local roads. So to deal with this issue, we had to go ahead and split the RIDIS data segment, the RIDIS features at every intersection. So we created these street intersections. These are the red points you see here, red dots on the screen here. And so everywhere you see a red dot, we split the RIDIS segment, the blue line. And in this example, we then take the 5-minute delay that's experienced for the full segment and then estimate each of the individual segments based on their specific segment length. So in our scenario here, we're going to assume each of these black dashes represents about 30 seconds of delay. So this idea here where each of these segments is based on the delay is based on the length of the segment. Let's go ahead and put that in a parking lot, and we'll address that in phase 2 of this project. So here we have an example of a school bus that enters the RIDIS segment from one of the horizontal lines, depending on which direction you're looking at it from, and then follows along the corridor, the RIDIS segment, for 6 segments. So there's 6 dash lines here that are in conjunction with the horizontal part of the RIDIS segment, and then it exits that corridor. Now, that school bus is in travel, but for the RIDIS data, the congestion data we have, since each of these dash segments are 30 seconds in delay, if we add those up, that gives us 3 minutes of delay that the bus experiences while it's traveling along corresponding RIDIS segment. So here we can look at a more complex scenario where we've added a couple transit routes and an additional school bus route. And so if we look at this top green transit route, it enters from the right-hand side, comes down, and it travels along the corridor of the RIDIS segment, 8 segments. All right, so this top green line experiences 4 minutes of delay. The second green line actually travels the full length of the RIDIS segment, so it experiences 5 minutes of delay. And if you add those together, you get 9 minutes of delay total for those 2 buses. On the school bus side, both these buses enter and exit at different points along the RIDIS segment. But in both cases, they experience 3 minutes of delay each. So in our scenario, we see that the RIDIS segment is causing 5 minutes of delay per vehicle. And on the school bus side, that gives us a cumulative impact of 6 minutes, 3 minutes for one bus and 3 minutes for the other school bus. And on the transit side, there's a total of 9 minutes cumulative delay, 4 minutes for the top green line bus, and then 5 minutes for the second bus. So this is kind of what we were dealing with and how we had to separate out these lines in order to combine all these data sets into a single final analysis layer. So the spatial inputs are here are some maps that show each of the 3 data sets and their different densities. So on the left-hand side is the RIDIS. Again, these are primary roads. So you can see it's mostly major roads. In the middle is the edulog or the school bus layer. You can see how dense that is. And it looks like there's a lot of roads that are being traveled on by school buses that are not included in the RIDIS. So a lot of those roads are excluded from the final analysis result. And then GTFS is probably more closely mimics RIDIS data. So there might be some local roads, but those are probably going to be fairly close to what RIDIS is capturing in terms of congestion. But you can kind of see that that has a lower density in terms of number of roads used than the RIDIS data set. Here is where we've kind of overlaid all 3 data sets together. And this just really kind of highlights the complex nature of combining these together in the end into a single final road layer. So some of the outputs we get from the final results, we get some daily delay profiles. We get one for both the school bus impact and the transit bus. So for school buses, we can see that we've got 2 big peaks in the AM and PM. So, the 7 o'clock starts at 6 o'clock and goes up to 8, pretty strong peak, and then drops down. And then in the afternoon, as students are heading home, we start to see another peak arise starting around 2 into 3 or 4, and then breaking off around 5 and then disappearing. So, this is kind of what we'd expect. There's not really much, if any, school bus travel in the middle of the day, from 10 to 12, 10 to 1. There's very little. There's going to be some, but there's not going to be a lot. And then clearly, once the kids are home, there's not really anything after 5 or 6 o'clock. On the transit side, we see similar peaks. They're not as high, but we do have the peaks in similar hours. So the morning peak is the same hour, 8 o'clock. The PM hours are shifted down an hour, but not by much. But we do see that they do have congestion impacts throughout the day, as they are providing transit services in the middle of the day. So they do experience that for a longer period of time throughout the day than school buses do. We can look at, so once we have these 3 data sets, we can calculate some network comparisons. So if we look at the RIDIS data set, we've got 372 road miles. So if you recall from that map, all those line segments add up to be about 372 miles. On the school bus side, that map was much denser. And so the total road that we have for school buses is 1,130. And due to the nature of how the sparseness of the RIDIS data set, we see that only about 178 of those school bus miles overlap with RIDIS segments. On the GTFS side, there's about 464 road miles, and about 220 of those overlap with RIDIS segments. Now, so these are just road miles, right? So these are just the length of the individual lines that you saw on those maps I showed earlier. But we can calculate the route miles. So for both school and public transit, multiple buses are traversing every one of those roads multiple times. In some cases, they're going multiple times over the same segment. So we see that that can greatly impact their route miles throughout the day. And so on the school bus side, route miles we calculated were about 27,000, almost 28,000 miles, and about 5,000 of those route miles overlapped with RIDIS segments. On the GTFS side, it's a much denser layer, but they also run longer throughout the day. So it's maybe greater than you'd expect based on that map. But we did see about 16,000 route miles, and about half of those, 8,400, overlap with RIDIS segments. So there's a significant number of segments that are not being included in the final analysis here, which I'll talk about when we get to the costs and the conservative nature of those costs. We can also estimate the minutes of delay. So on the RIDIS side, we estimated about 1,450 minutes of delay per vehicle. And then on the school bus side, it was almost 3,400 minutes. And on the GTFS side, 4,500 minutes of delay, daily delay. And again, those are only on routes that overlap with RIDIS data where we had congestion information. So some quantitative results for Durham. These are conservative estimates. As I've said, we saw that there's a significant number of school and transit routes or roads, route that do not traverse the same routes as RIDIS, that are not included. So any of these estimates we have here are on the conservative side. The transit operating costs, I'll get to that. So the RIDIS segments, so the 1,450 minutes is about 24 hours, vehicle hours of recurring congestion delay per day. On the transit fixed route side and the transit side, those 4,500 minutes corresponds to about 75 hours of delay per day. And that corresponds to about $7,200 in daily operating and capital expenses. So if we extend that out to a yearly impact, we take the 4,500 minutes, we divide it by 60 to get the number of hours, and then we multiply that by $95.89 per hour. And that was provided to us by the transit system, Go Durham. And then just estimate a typical year of 250 days. That gives us about 1.8 million in annual expenses from recurring congestion alone. And that corresponds to 785 tire days of total yearly weekday delay. So all those hours, 75 hours per day corresponds to about 2.1 years yearly. On the school bus side, we get about 57 hours of delay per day. That corresponds to $4,200 in daily operating and capital expenses. And that gives us about $784,000 in annual expenses from congestion. And we used an estimate of $75 per hour there. We didn't at the time have an exact cost, so just estimated that value. And that 57 hours per day corresponds to 442 days of delay per year. Okay, so what are some of the unaddressed issues from phase one? So the focus of phase one was to understand when and where school and public transit buses were most impacted by congestion delays. But some of the things that we didn't address were, do the buses cause the delay, right? So again, we need to understand where this is occurring, I think, before we can understand if the buses are causing those delays. So we didn't look at that cause or that issue. Another issue, which is a big one, is how much delay is on segments that we don't have congestion data for. So that goes back to the sparseness of the RIDIS data set, how many riders experience the delay, and what is their value of time. So we do have access to ridership data. So that is something that future research could address, could look at the impact on rider experience and what their value of time is and what the cost of their value of time is. How do we account for existing treatments to help buses avoid congestion? So again, I proposed several different options, but we did not look at how to apply any of those options at specific high congestion corridors from the final results. This does assume that there is an adherence to the scheduled route. So this is obviously mostly, if not all, on the school bus side. So I don't know if you caught it earlier, I talked about that the route is based on the planned route, but it's possible that the driver could take a different route. And this would be especially the case in the afternoon if certain kids have after school activities and don't take the bus home, could drastically change the nature of how that route runs. So we're assuming that they're adhering to the planned or scheduled route. We did not look at summer school routes. We did not consider weekend congestion, and demand response transportation was not considered as part of this research project. Some of the drawbacks, I've touched on a few of these, but I'll kind of go over these again. So again, and this is probably the biggest one, is that there was a large percentage of roads that were not included in the RIDIS data set for us to get a comprehensive look at the congestion across the full county. And based on the density we saw, this probably mostly impacts the school bus, but public transit could also be affected by this as well. There's the issue of proportionalization of the RIDIS data set. So if we know the segment, the delay along the segment, we are just proportionalizing that based on the individual segments after we've split them out, rather than what the actual congestion is along each of those individual segments. The process is based on an edulog data set or output, but that is one of many software vendors utilized. So we just developed that using edulog. So it might be a drawback if there's different outputs from other vendors that don't fit into that method we set up. And ultimately, it's a very difficult process to automate or replicate. There was a lot of manual effort in geocoding the school bus route. I'm not going to get into that, but there was a lot of effort there that went into prepping the data sets to get to the final analysis layers. So those are some of the drawbacks. Some of the things that we talked about for future research from phase one would be to create standards for roadway congestion, school and transit bus data, incorporate bus ridership data, explore using GPS or AVL data for bus routes, increase the accessibility by developing web-based tools for data analysis, and then expanding the web mapping tool output. So we'll talk about the web mapping tool at the end of the demo, or at the end of the presentation. So phase two goals, from the previous slide, we saw a lot of things that we could consider for phase two, but we thought that the best approach would be to try and find a better methodology to determine when and where school and public transit buses are most impacted by congestion, and to see if we could develop a tool to be used by practitioners to understand that. So that's what we focused on for phase two. And so in order to simplify the methodology, the school bus and public transit bus side had to be changed drastically. So one avenue that we thought would be a good place to look at would be the growth in AVL data. So public transit and school buses are starting to capture automatic vehicle locator data on the vehicle's GPS data. And so if that data is becoming more standardized, more utilized, then that would be a simple way to set this process up. And so we developed a standardized input schema based on this assumption that AVL data is available and will become available. The second goal for phase two was to find a more robust congestion data set, hopefully one that would cover at least a larger percentage of the area, and also maybe address the segmentation issues that we had to deal with the RIDIS data set. And then the final part was to develop a standalone tool that we could share out with transit planners who could input their own data sets and then run the analysis on their own, and then go from there in terms of determining treatments and ways to alleviate or address those congestion issues. So for phase two, this is our study area, this black line you see here. So this is a subset of Durham County. We picked an area that some of our researchers were familiar with, but it also included several public transit routes, schools, and school bus routes. So we wanted to ensure that we had all three of those, both of those plus the congestion data. But we also wanted to kind of focus on just a small area for the development of the tool. For the road reference layer, so this was kind of a key part. So the road reference layer would be used to create the routes for the RIDIS data set, the school bus routes, and the transit routes, which means we'd have a single feature class that would be used for all three data sets, which would make it easier to combine them back together at the end. So that was our starting point, was a single road reference layer. And we created a network data set from that reference layer. We split it at the intersections, at the junctions, and then we captured the congestion data for each of those segmented roads, or those split segments. And then we kind of pieced together the schools based on the AVL data and that split segment route layer. So here is just kind of a picture. It's kind of reinforcing what we did in phase one. So for congestion, so one of the big issues was trying to find if there was an alternative to the RIDIS data set. So I covered these, lack of full coverage, not available between every intersection, and RIDIS can be expensive. So we were lucky enough to obtain this data through NCDOT, but getting this yourself could be an expensive undertaking. Some alternatives that we looked into to RIDIS were Mapbox, ArcGIS traffic data, Outscraper here, and Google Traffic. And some of the metrics to consider when choosing your congestion data source: make sure that they have satisfactory data source outputs. That includes minutes of delay, the data types, format, etc. Easy to use, that's a big one. The cost, depending on what you have. In terms of funding available, cost might be a prohibitive factor. And then the origin of the traffic data. So those are some of the metrics that we considered when determining what we wanted to use. And we agreed to use a program called Outscraper. There are several or open source options available, but ultimately Outscraper had several things going for it. It was the simplest interface of those that we looked at to capture the congestion data. There is an API available to connect to a web application. So if we were to develop some web application in the future, we could use the API directly. And it's the only source that we looked at that did not require additional proprietary software. So we went with Outscraper. Here is kind of what the interface looks at. It's a fairly straightforward process. So basically, all you have to input are coordinate pairs or intersection names. So it's looking for a begin and end coordinate. So in this window here where you see these X and Y coordinates, one column is a list of begin coordinates, and then the second column are the end coordinates of each segment that you want to know the congestion data for. And it's going to give you the travel speed, the travel time for that segment. So we captured begin and end coordinates for every segment that we created from the split network data set. We copy and pasted those directly into here. You can also upload a CSV file and then select your date range and your time interval and then get your data. And I don't remember how long it takes. So it's not too bad depending on the size, but we had a small data set, so it didn't take too long. One drawback to be aware of is when it spits back your information, the output, which I'll get to in a second, you can't give this a segment ID. So there's no easy way to join this data, the results from running it through Outscraper back to your original data set. So that was one issue with this that we had to find a workaround, and we did, but just be aware of that. The output from Outscraper, so this is just kind of the data dictionary of the fields that are included in the file you get from Outscraper. It's a CSV file, and several of these fields we used as part of the process to get the information back to the reference layer, specifically the road distance timing field. So that's where we captured the travel time for every segment that Outscraper provided to us. So here is an example of kind of how Outscraper works. If you recall back to the example I showed earlier, where we were looking at the RIDIS segments. So here, what we get, instead of one segment from beginning to end, giving you the congestion delay, here we get the travel time for each of these segments separately. So it calculates for each of these, between each of these red dots, what the travel time is directly, right? So we don't have to proportionalize any of that information. It's all done for us by Outscraper. And here is just a way to kind of compare the two methods. So this was a big advantage for us, was that it's obviously a much more accurate reflection of the delay, since it's not based on the length of the segment, it's actually based on the delay that's calculated through their source. So here's just an example where, we see here at the bottom, it could be that this last dashed line was the biggest culprit of the delay across the whole thing. But if we applied that through RIDIS, it would only show that it was a small portion of it. So Outscraper definitely provided some much more accurate congestion-related data for us than we saw with RIDIS. And it also covered every road segment. So it's also, and two fronts was a much better option. And here is just a quick map of our study area showing the minutes of delay per vehicle. So that's what we calculated directly from the Outscraper data set. On the school and public transit side, so again, we talked about it at the beginning. So they're very similar in how they operate. They've got fixed stop times and locations, and they're served daily. And so with that, if we can develop a schema for both, apply it to both, then we only need to create a single methodology to analyze both data sets. So we don't have to do those two separate methodologies for each. And so we developed a standardized schema. So here is our proposed AVL, automatic vehicle locator data schema for both school and public transit buses. So these fields would be included in both. This is what we would need. The method we created used this schema as part of its methodology. And just a quick note, so some of these are optional, and we did kind of include GTFS or think about GTFS and what they asked for. So some of these align with what GTFS already has. So there is some overlap there in the schemas. Once we have that schema, we can create the routes using the network data set. And here you see the outputs from that. So we've got 3 maps that we put together that show you what the school bus frequency is on the left. And we're just looking at a single hour here, but this could be run for any hour of data that you collect congestion data for, and school bus and public transit frequencies. The middle map shows public transit frequency, and then the last map on the right combines those 2 together to understand where we might see the most impact for both school and public transit. And then once we have the frequencies and we got the congestion, the minutes of delay earlier, we can combine those 2 things together to figure out what the minutes of delay by mode are. And this is cumulative. So we take the frequency and multiply it by the minutes of delay per vehicle to get the cumulative minutes of delay. And here are that study area again, where we show the minutes of delay at 7 o'clock for each of those 3 data sets. So the school buses on the left, public transit in the middle, and then combine the 2 together on the right-hand side. Okay, and I would like to turn it over to my coworker, Narmina, who will talk about the tool that we built that does all that.
Hello, everyone. So in order to make it more automate the process and make it easier for planners, we were thinking about delivering some easy-to-use toolbox, which currently is developed within the ArcGIS environment and is written in Python. So currently these tools go as a chain of inputs and outputs. So basically we start with our segmented reference layer, and currently we do need to upload the segments, like segmented roads, and that helps us to prepare Outscraper Input query, where we have this beginning and end coordinates of the segment, and we do some pre-processing of the Outscraper results in order to feed the future inputs. So next inputs, we use the school bus and transit AVL data that we request in the defined schema that Jeremy just previously identified and showed us. So that AVL data is, since it's already within the schema, we have bus frequency tool, which considers school buses or transit buses as the same, so we can run them separately. So within the tool, we build a network data set and use network analyst extension of ArcGIS to make the routes using AVL stubs. And then later we split those routes in order to feed those road segments, so we can join into one feature class and continue our calculations in order to calculate the frequencies. So, and after that, since we already have the congestion data from Outscraper that is prepared, and then frequencies from buses and from transit buses and school buses, and we can upload them into the final minutes of delay calculation tool, which will eventually give us this output where we can have all of the listed above and showed on the maps results of congestion and minutes of delay per vehicle and total basically congestion of school and transit data sets. So currently we use the Python script and ArcPy library within ArcGIS environment, so it's proprietary, as well as network analyst extension is required in order to run the tools. So ideal and consideration is that those tools can be available through web map application, where a particular planner doesn't have to have an access to software, but can just log in the WebGIS application that has all those geoprocessing tools available to them. And as Jeremy mentioned, ideally being able to query the data from Outscraper within the environment. This tool will be is available by the request, and we'll be happy to provide some demo and introduction to it. I think now we can go to the next slide, where we can show what can outputs look like within the web map environment and web map application. And we did this for phase 1, where we had both studies areas mapped as a temporal visualization. So it's a temporal mapping where, since we have congestion data available per hour per segment, so we can see the patterns visually. And So those outputs allow us to visually see the congestion and high congestion areas that we can bring to attention and in talking and policymakers, and in order to have better planning too.
But basically there's the maps I showed you, we've got a layer for each of those maps. So to show you the minutes of delay per vehicle, the cumulative minutes of delay by school bus, public transit, and then combine the two together. And it's got a time slider, which will show you throughout the day, by hour of the day, where high congestion corridors are occurring.
Mhm.
So that's what we were hoping to share. And so that data set through phase 2, we can also display that information through here.
So basically that's the outputs, and this is the time slider, which available as a widget.
We apologize for that. We can certainly, if anybody's interested, we'll get that figured out and get the link sent to you. Yeah, real quickly. So we did have there's some future research from phase 2 that we could factor in some environmental and societal costs into our overall costs. So we looked at just the operating and capital expenditures. One of the things that we saw in phase 1 that could be done that we didn't do in phase 2 was incorporate bus ridership. The toolbox that Marina's worked on has to be used within Esri's desktop software. So, ideally that could be migrated to a web application for those that don't have access to that desktop software. And then can increase accessibility by developing additional tools for data analysis, and then expand some of the web mapping tool outputs. So those are some things that we could do in the future. And that's it. So we are happy to take any questions from the audience.
We have one question.
So Maggie asked, as a student, what would you want my classmates and me to know about a career in this area? In which area? Transit and GIS, congestion, planning. So, there's lots of different avenues that we kind of covered, which I guess would be one nice thing about this project is that it's not a single focused work, right? It's things that you can apply in multiple areas, but it covers public transit, school transit, and congestion. Thank you, everyone.
Thank you.